Yes. And we are back live once again. And a cheer goes up across the land of Barnegat. People shouting out their windows. It's time. It's time for math class. I assume that's what's happening. I can hear your chants outside my window. Yeah, I'm just assuming that's what's going to happen. So, welcome back once again. I'm giving people a minute or two to get in because my Chromebook does say 927. And up there, it does say like 929. Oh, now it says 928. But giving people a few minutes to kind of get into the live stream, that would be fantastic. If you would be so kind to leave a comment in the chat so that I have that from my records, that would be fantastic. Yeah, just leave your comments. Yeah. At some point, I saw this chat up towards like 8 or 9 people, and now it's only down to like 5 or 6. So there goes some people leaving some comments. While they're leaving their comments, and thank you for that, I appreciate that, I'm going to tell you how today's class is going to be running. First, I would like to review some of the information that we have been doing for the past week in regards to simplifying radical expressions. That would be fantastic, and I would love that. Beyond that, I would like to take a step in a slightly new direction. I say slightly new because we're going to be utilizing the skills that we have been building up over the past chapter in order to learn something slightly new. I'm going to give you all the heads up right now, and I'll give you the heads up a little bit later, that I am going to be assigning you something before I leave this building here today. That is going to count as a grade, of course, but it is going to be based on the simplifying of radicals that we have been doing, which is fantastic. So I would appreciate that. And when I assign that, of course, that people would get that done. But I am going to be assigning it today. I'm probably going to be assigning it during fourth period because fourth period I usually cover study hall. But obviously there's no study hall to cover today. So I am going to be assigning that probably before lunch. So just giving y'all the heads up on that. Directions will be in the Google Classroom. Anyway, here we are. Everyone having stayed up late and watching the game or the commercials or whatever it is that you ended up watching. I really don't care. But it's just, everyone else gets to stay home. I have to come in here today and teach to an empty classroom. I feel lonely and sad and crying on the inside. I don't know. Whatever. But anyway, in lieu of that, ladies and gentlemen, what I would appreciate from you, because I do see all the wonderful comments that I got on the side right there, and I see the 12 people so far, hoping 13 people so far in the chat. I'd love for that number to pop up even more. If you would, I'm going to need those notebooks out and open. Let's do it. Woo! I got to get hyped without anybody in the room. That's so sad for me. It's not that hard to get hyped. Oh, goodness gracious. As always, I do have the chat open right where I'm sitting. So if you do have any questions as we're moving along with this, by all means, you can ask those questions, and that would be fantastic. Right now, I'm working off of the same worksheet that we have been working on the past several class periods, and that is worksheet 6.6. Now, in the Google Classroom stream, I had posted this particular PDF of worksheet 6.6. In fact, I can show it to you here. Here's our Google Classroom. If you scroll down a little bit, you will see PDFs. I posted them originally on January 29th. I may have posted them a bit early, but that's okay. But I posted them, practice worksheet 6.5 and 6.6. They are in the Google Classroom stream, just in case you need them. I am going to be posting something slightly new today, but I am going to be picking my problems off of this particular worksheet, and that'd be fantastic. So we'll get there. Anyway, so this is going to wrap up simplifying radical expressions, and then I'm going to, like I said, I'm going to be getting into something anew today, which I'm kind of excited about. So anyway, because I know we've been solving these, simplifying these radical expressions like what feels like forever, but in reality, it's only been about a week. It's been in like maybe 3 class periods or something like that. Regardless, here we are. So this is simplifying radical practice. Simplifying radical practice. Boom, there we go. And of course, I'll do my best to avoid that glare. So, let's try a problem like this. Example. And I'm taking these off of the worksheet. You use that worksheet, obviously, as practice, but I'm going to change the variable to an x to make it a bit easier to look at. But this is actually problem number 19 off of that particular worksheet. Number 19. Okay. Now, I say solving radical practice, but you don't see a radical symbol up here. As we've been learning for several weeks now, when you see this fractional exponent floating around this problem, this fractional exponent is in reference to a root. Now, what type of root do we potentially have? Well, in this particular problem, we have a fourth root. Fourth root. Because when you see that fractional exponent, I want you to be aware of the fact that that fractional exponent is, of course, power over root. The power being the top of the fraction, the root being the bottom of the fraction. Now, there are several directions that we can go with this particular problem. Several directions. And technically, as I have talked to you about, there is more than one way to do a problem like this. There is way more than one way to do a problem. I'm not saying that the way that I'm about to show you is the best way, but it kind of is. Anyway, you could convert these two terms being multiplied together. You could convert them into radical form because technically they both have the same root. Now, watch what I'm about to do here. Where's my marker? I want my orange marker. Where did I throw you, orange marker? I got you. Yeah. Now notice, I'm going to put this up on the board in dry erase marker because I'm going to erase it when I'm done. I am not going to put this into my notes. I want you to see what I'm about to show you. Check this out. Now, again, this is one way of doing the problem, and it's valid. You could convert the problem to radical form because, well, they're both a fourth root. And since they're both fourth roots, I could put them together into a singular fourth root. Now, again, I just want to reiterate, I'm writing this in dry erase marker. I'm going to erase it in a moment because this is not what I'm going to put into my notes. If I put them together, this would be x cubed times x to the 13th, x to the 3rd, x to the 13th. That's really x to the 16th power. Now, it's a fourth root. The only way to escape a fourth root is by having a perfect fourth power. Well, this is a fourth root of x to the 4th, x to the 4th, x to the 4th, x to the 4th. This is a very long, drawn-out problem. And I'm just reminding you, I'm going to erase all that because that's not what I'm putting in my notes. But this x can escape, this x can escape, this x can escape, and this x can escape because they all have the proper exponent. There are 4 x's that are allowed to escape that are all being multiplied by each other, resulting in x to the 4th power because there's nothing left on the inside of the radical. Let me recap what I just did, and then I'm going to erase that and show you a much nicer way of doing the problem. It's a strategy. First, you could convert the problem into radical form because they both have a fourth root on the fraction. fourth root. You could bring them together into a single fourth root because they have the same type of root, which is fantastic. That's a property that you are allowed to do when there is multiplication division between them. Bring them together to be x to the 16th because you add the exponents together. You could break that x to the 16th up, x to the 4th, x to the 4th, x to the 4th, x to the 4th. And because they have the proper exponent, they are allowed to escape that fourth root. X times x times x times x would give you your final answer. But as I've promised multiple times, I'm erasing that and showing you a much nicer way of doing it. Sometimes, if you can recognize the shortcut, you should take the shortcut. See, what ends up happening is when you have these two terms being multiplied together, the exponent property is that we add the exponents. You are to add the exponents together. Well, they're fractions, Mr. Markey. I know. They're fractions with a common denominator. And since they're fractions with a common denominator, I can bring them together to be x to the 16 over 4 exponent. X to the 16 over 4, the 16th power, the fourth root. That's just what I did in orange, except I got there a lot faster. Wait a minute. 16 over 4, doesn't that reduce? Yes, it does. 16 over 4 just becomes x to the 4th power. And the problem is done. And again, cheers. Just all I'm hearing are cheers. People high-fiving each other. Brings a tear to my eye. Not all problems are as easy as that. Not all problems are going to be as easy as that. They're not. Your job is to recognize when you can and cannot take those shortcuts. That's what this practice is about. Let's try. Ooh, that's a good one. Let's try this one. This is one, again, directly from that worksheet, 6.6, that is in the Google Classroom stream. It is actually problem number 24. T to the 2/3 power over 5 times t to the 1/2 power times t to the negative 3/4 power. I'll move that out of the glare. There we go. Zoom in a little. There we go. X to the 2/3 on top. On the bottom is a coefficient of 5, a t to the 1/2, and a t to the negative 3/4. That's a negative 3/4. But Mr. Markey, I was taught a very long time ago that you're not allowed to have negative exponents. Well, you're partially right. You're not allowed to have negative exponents in your answer. Negative exponents in the middle of the problem, that can happen. And sometimes that's kind of acceptable, but we'll deal with that. But let's deal with the exponent properties. Now, everything is being multiplied or divided here. Everything is being multiplied or divided here, which is acceptable. Would it be beneficial for us to convert to radical form? Well, not necessarily. I could potentially combine these things as they are. I could. They don't have common denominators, though. Oh, what was the exponent property? Oh, I remember. When you are multiplying common bases, you add the exponents. When you are dividing common bases, you subtract the exponents. You got to look back at your exponent properties. We wrote these down I don't even remember how long ago, but they are in your notes. I can point you to the lesson in the playlist, in the YouTube playlist. I should post that later. But let's deal with this a piece at a time. First, since I'm going to be combining these common bases by adding or subtracting their exponents, I think it would be in our best interest if we found common denominators for all three of them. The top denominator is 3. The bottom denominators are 2 and 4, which means that our common denominator would most likely be 12. I mean, most likely it is. So, let's try it. Let's do it. So I'm going to have to rewrite this problem as t to the 8 over 12, because I'm multiplying that by 4 and 4 to get the common denominator, over. This 5 is just going to hang out for the time being. The 5's not really going to do much. T to the 6 over 12 times t to the negative 9 over 12. It is in our best interest to find those common denominators, since we know that we're going to be adding and subtracting certain exponents. Now, again, two options that you have. You could take care of this all in one shot, or you could take this a piece at a time. You could take it as, well, I'm going to add these two together on the bottom first. Okay, you could. You absolutely could. I'm going to take a slight shortcut. The shortcut that I'm going to take is I am going to utilize the fact that this is division, meaning I have to subtract the exponents from the bottom. So it would be, in order to combine those t's, I would have 8 over 12 minus 6 over 12 minus negative 9 over 12. Because it's this original exponent that you are subtracting from. You are going to subtract that 6 over 12, and you are going to subtract that negative 9 over 12. Mr. Markey, subtracting a negative, doesn't that do something? Yes, it does. Mr. Markey, what's that 5 going to do? Nothing. That 5 is literally just going to sit there the whole time. And I want you to note that that 5 is on the bottom of the fraction. That 5 is going to stay in the bottom of the fraction. That 5 is going to do nothing. It's going to stay in the bottom of the fraction. But let's deal with the rest of those exponents. We have to take the 8 over 12, subtract the 6 over 12, and subtract the negative 9 over 12. Let's see what happens. So, little note for myself at the bottom. I'm going to have to do an 8 over 12 minus 6 over 12 minus a negative 9 over 12, which, yes, that will be plus. So if I did all of that correctly, this should give me an 11 over 12. Huh. So let me write that out. This problem will turn into the following. T to the 11 over 12th power with that constant of 5 still sitting on the bottom of the problem. That's so messed up. I know, it is messed up, isn't it? Now, this is one way of writing the problem. I'm going to show you an alternate way of writing the answer in a moment. Technically, this is the simplified answer. Mr. Markey, how do you know it's simplified? Ooh, let me show you the alternative way, and you'll know why. But let me just recap what I just did. This was the original problem. I saw all the t's that were going to be combined. I'm going to have to add and subtract exponents to get them to work out. But, common denominator. First thing I did, I found a common denominator for all 3 exponents. And then as I've argued, well, Technically, you're supposed to subtract the exponents if they're being divided. Yeah, technically, you're supposed to add those two, but you could do this all in one shot. 8/12 minus the 6/12, 8/12 minus the -9/12, which would become plus. Here are the three fractions. It would be 8/12 minus the 6/12 and minus the -9/12, which ultimately gave me 11/12. Here's the alternate way of writing the problem, of writing the answer, I should say. Now, why is that the alternative way? Power over root. It's an 11th power. It is a 12th root. So I put the 12th root with the t to the 11 on the inside. Again, what's that 5 do? The 5 does absolutely nothing. It just sits there on the bottom. But how do I know I'm done? How do I know I've simplified it? Well, the only way you escape a 12th root is if you have the appropriate 12th power. It doesn't have enough. This t to the 11th does not have a proper exponent to be able to escape a 12th root. Simplified. I'm going to show you one more problem before I get to the main lesson of today. One more practice problem before I show you the main lesson of today. But in all honesty, how do you know you're done? If you convert it to radical form, you can check to see if anything can escape the radical. And if it can escape it, then you must reduce it. You'll see more of that on the very next problem. And like I said, one more practice problem, and then I will begin the actual main lesson of what I needed to do today. Let's see what we got here. On that same page, example, it's actually number 27. Okay. The square root of 12 and the fifth root of 12 to the third power. That is not a typo. They have different roots. And because they have different roots, I cannot put them together. They have different roots. One's a square root, one's a fifth root. I can't put them together. What does one do? Let's convert it to be a fractional exponent in the guise of power over root. This should really be 12 to the 1/2 power and 12 to the 3/5 power. Nothing has changed except the way the problem looks. It's still a square root. It's still a fifth root. It just looks different. And the reason why it's better for you to convert to fractional exponents, number one, they don't have the same root. But now, base of 12 times base of 12, I'm supposed to add the exponents together? Yes. But Mr. Markey, they have different denominators. Yes. So you have to find a common denominator. 2 and 5, common denominator, 10. So this should really be 12 to the 5/10 power times 12 to the 6/10 power. Let's move that out of the glare a tiny bit. There we go. Add those exponents together. It should give me a 12 to the 11/10 power. But you're not done. What? How do you know? I'm going to convert it to radical form in a moment. And I'm going to show you how I know. But let's just recap. Number one, you can't combine the exponents at the beginning. You can't combine the exponents at the beginning of the problem or not the exponents, the radicals, because they do not have the same root. One is a square root, one is a fifth root. Can't do it. So I converted them to fractional exponents. Oh, I'm supposed to add the exponents together. Yes, you are, when you have common denominators. When you found those common denominators, you added them together, you got 11 over 12. Yay! Let's convert it back to radical form. Power over root. This should be a 10th root of 12 to the 11th power. I'm going to zoom in on that, actually. A 10th root of 12 to the 11th power. How do I know I'm not done? Well, how does one escape a 10th root? To escape a 10th root, you need to have a 10th power. This is 12 to the 11th power, meaning there are 11 of them floating around. I can split that up. I can split that up in order to force a 10th exponent. I can do the 10th root of 12 to the 10th power and 12 to the first power. Yes, you can. Because that would give you the 11th power. This 12 is allowed to escape because it has the proper exponent, as we've done 100 times in the past, giving you 12 10th root of 12. That, believe it or not, that monstrosity of an image is the simplified answer to this problem. The general rule of thumb is this. How do you know you're done? How do you know it's simplified or not? Convert it to radical form and see if anything escapes. That is your rule of thumb. Okay. Now, like I said, I am going to be assigning you something in regards to simplifying radicals before I leave the building here today. I'll probably assign it before lunch. It will count. It'll get you the practice that you need, and I'll be able to see where you guys are at. In the meantime, I'm super hyped for what I'm about to show you. I am introducing to you a slightly new concept called solving radical equations. Since the dawn of man, since cavemen first looked across the field, they thought to themselves, how can I solve for x? That's literally what they said to themselves. I'm going to post in the Google Classroom the worksheet that I would like to work on today. Oh, that's the wrong one. Hold on. This is the right one. Yes. PDF for today. Post. There it goes. It should be getting to you in a moment. But this particular PDF are the problems that I'm going to be working off today. I'm going to be referencing the problem number. So if you need to see it more clearly, you can, of course, go to the practice worksheet 6.7. And we are going to be working off of these particular problems. So there are going to be a few rules and caveats that I have to address. And I'm just going to start with the first one. And it is so important that I'm going to give it a star, Now, I know I write that star and you guys gasp because you're like, a star. He's only done like 8 of them this year. I try not to do that many. But when I write this star, you better believe that the statement that I am about to make is going to have huge ramifications. If you introduce an even root to solve a problem, this is an if-then statement. If you introduce an even root, and I'm underlining the word even root. If you introduce an even root to solve a problem, you must include a plus or minus. You must include a plus or minus. And I'll show you what that looks like on a few of the example problems. But again, it's if you introduce an even root into the problem. The key phrase is if you do it. If the problem already had an even root, if the problem already had an even root floating around, then you don't have to worry about a plus or minus. I'm trying to get some papers here. There we go. I do have a few examples of such that I am going to be throwing at you in a little bit, but let's start with some of the more basic things. Just got to get to the right page in this little example that I have here. Ha-ha! There you are. Okay, putting you aside. And that just flew in the trash. That was great. That made me smile. Back to this. So starting very simply, I'm going to throw out problem number 1 off of that worksheet. Problem number 1. I'm going to have an alternative number 1 in a minute, but let's start out with this. Square root of x equals 8. Now, for this particular problem, again, the square root is already there. And since the square root is already there, you do not have to worry about a plus or minus. Did you introduce it to the problem? No, you did not introduce it to the problem. Now, there are several ways to kind of go about this problem. I'm going to go through literally the most simplistic way of thinking about it. This is a square root. How does one cancel out a square root? Well, Mr. Markey, you cancel it out by squaring both sides. Yes, you do. And when you square both sides, it will cancel out that square root. Let's see. I'm actually going to write it out long ways. So square root of x would now be squared, but whatever you do to one side, you must do to the other. So that 8 is also squared in order to keep things balanced. That square root and that square will mutually knock each other out, leaving you with x. And on the right side of the problem, well, it's just 64. Yes. Mr. Markey, that seems way too easy. Yes. It is. It just is. Just one of those things. Like, what the heck? I know. But that's all that the problem had to do with it. Let's take a look at an alternative one. Now, I say alternative one. When I'm going to use an alternative one, it's going to be different, not on the worksheet, but slightly different than the one I just did. So this is number 1 again, but it's going to be an alternative. So I'm going to put alt. Alt. X squared equals 64. So Marky, how is this a radical problem? How is this a radical equation? I don't see a radical in there. I know. But your job is to solve for x. Solve for x. And since you're solving for x, you're trying to get x by itself. Your goal is to get rid of that exponent. Well, how does one get rid of a exponent that represents something being squared? Oh, you square root it. And whatever you do to one side, you have to do to the other. Wait a minute. Wait a minute. Wait a minute. Mr. Markey, you introduced a square root into the problem. By golly, I did. I did introduce a square root into the problem. Mr. Markey, you just said before that if you introduced a square root into the problem, that you had to do something. You put a star next to it. It's so important. I did. I did indeed. I need a plus or minus. And I'll go over the rationale as to why that is in a moment. But you need a plus or minus. Where does one put the plus or minus? You're going to put that plus or minus. I'm going to zoom in on that. You're going to put that plus or minus on one side of the problem, typically the opposite side of where the variable is, typically. But that's what you're going to do. The square root of 64, I know it's 8, and that plus or minus is still there. The square root of x squared on the left side, they cancel, leaving you with just the x. Yes, indeed. Let's look at these two problems. Let's look at these two problems as a whole. Because these two problems are opposite sides of the same coin. These two problems are opposite sides of the same coin, and you have to recognize that fact. We got an answer of 64 in the first one. How does one check to make sure that you're correct? You plug it back in. I'm going to take that 64, plug it in right there. The square root of 64 is equal to 8. It works. Cool. What about the second problem? Well, I know that 8 squared is 64. Yeah, 8 squared is 64. Good for you. So is negative 8. If you take that negative 8 and you square it properly, putting it inside a set of parentheses, of course, negative 8 in parentheses squared will also give you that positive 64. It doesn't work up here to do a plus or minus. First of all, there is no plus or minus in front of that radical. That radical was already there. So you don't have to worry about that plus or minus. Second, you don't need a plus or minus in front of the 64 because you did not introduce a square root to the problem, or an even root, I should say. And if you tried to do plus or minus, plugging it back in here, if you tried to plug in a negative 64, it's not going to work. Square root of negative 64, your calculator would say, because that would be a non-real solution, a complex answer that would not give you the answer of positive 8 that you were looking for. Let's try another one. Let's try off of that worksheet. Number 9. Example number 9. Number 9 is 6 plus the third root of q minus 4 equals 9. I'm going to let you in on a secret. PEMDAS is kind of taught slightly incorrectly, but that's not the secret. PEMDAS can be used in a particular way in order to help us solve this problem. The way one solves a problem for a variable, in this case the variable q, is you have to peel off the outside layers using PEMDAS backwards. You know PEMDAS. PEMDAS is the order of operations. Please excuse my dear Aunt Sally. Parentheses, exponents, multiplication, division, addition, subtraction. That is PEMDAS. That is the order of operations, and that is how one simplifies or evaluates expressions. However, when one solves an equation such as this, you have to peel off the layers in a very particular order. And the order in which you peel them off is PEMDAS backwards, or SADMAP. SADMAP, trademark. I said trademark, so now I own it. But it works the same way as PEMDAS, just backwards. You take care of any outside addition, subtraction. Then you take care of any outside multiplication, division. Then you take care of any exponents. And then you take care of parentheses last, if the parentheses are on the inside of the problem, of course. There are two things that you have to recognize about this problem. Two things. Number one, there are parentheses. The parentheses are right here. You have to recognize that those are indeed parentheses, even though they're not in the original problem. Second, you need to recognize that a radical, a root, falls under the category of exponents. You need to recognize that. Because when you have a radical, when you have a root, in this example, a third root, as I've told you for multiple class periods, you need to recognize the phrase power over root. Power over root. Power over root. Oh, it's an exponent. That must mean it falls under the exponent category. Yes, it does. The way that one solves this particular problem is by first subtracting 6. Because if you're doing SADMAP to solve this problem, you're going to subtract 6 first. This will leave you with the third root of q minus 4 equals 3. So far, so good. There is no outside multiplication division to deal with. Mr. Murky, what about that minus 4? What about that minus 4? The minus 4 is on the inside of a set of parentheses. You can't touch that. You can't touch it yet, but you will later. Right now, we have to deal with exponents because that root is the next step of the problem, the next outside layer that we have to peel off. How does one get rid of a third root? Well, you raise both sides to the third power. Did you introduce an even root? Nope. I introduced an odd power, but I didn't introduce an even root. Then you're good. On the left side, they cancel. On the right side, you evaluate it. Now notice my parentheses went away because now I'm at my parentheses. Now I'm inside the parentheses. I've finally gotten to that set of parentheses that's on the inside of the problem. And finally, I can deal with that 4. I'm going to add 4 to both sides. And I get my answer. I get my answer of 31. Now I'm going to double check my answer in a moment. I'm going to make sure that I'm correct. But this is the process that you would have to go through in order to get that variable by itself. It's wonderful. So let's double check, make sure we're correct. First of all, I'm going to take that 31. I'm going to plug it back into the original. Order of operations now. I got to follow PEMDAS to evaluate this. 31 minus 4 is 27. The third root of 27, as we've talked about multiple times, is 3, because 3 times 3 times 3. 3 plus 6 is 9. It works. Wunderbar. It works. Can't believe it worked, but it worked. Well, I believe it worked. But whatever. Shut up. Anyway. I have an alternative problem for you. An alternative problem that's going to kind of throw this thing on its head a little bit. It's going to look much, much different than what I've just shown you. But we will be able to deal with it. Here is an alternative example. X to the 4/3 power minus 5 equals 11. This alternative example is really going to be helpful. So, there's only 2 things preventing me from getting X by itself. One of them being the 4/3 power, and one of them being the minus 5. Exponent, addition, subtraction. There's no multiplication, division. There's no sets of parentheses. I got to add 5 to start this problem. All right, I'll add 5 to start this problem. There we go. I added 5 to both sides. Whatever you do to one side, you got to do the other. But what now? Ooh. There are several ways I can handle this problem. As I've stated at the beginning of class, there's more than one way to solve these kinds of problems. There's more than one way to get the Tom's River. There's always more than one way to skin a cat. Each is just equally disgusting. Now notice that I am writing this in my orange dry erase marker. In fact, I'm going to rewrite it so you can see it because it's in the glare right now. There we go. But I'm going to erase it. I'm going to erase it because I don't want it in my notes, simply because it'll take too long in the long run. We'll see what happens here now. I could convert this problem to radical form. I absolutely could convert this problem to radical form. It is in the power 4/3, power over root. It is a third root. It is a 4th power. How does one get rid of a third root? Well, we cube it. And then we get x to the 4th equals some ginormous number. Oh, I don't want to deal with some ginormous number. Yeah, you could do that. What is 16 cubed? I don't think I have 16 cubed off the top of my head. 16 cubed. gosh, it's like 4096. Are you kidding me? This is a terrible way of doing the problem, Mr. Markey. I know. It's a good thing I'm going to be erasing this in a minute. Because remember, I'm going to show you an easier way to do it. But here's the key. What I'm about to show you is the important part. The only thing preventing you from getting this x by itself is that fourth power. How does one get rid of a fourth power? You have to introduce a fourth root. And when you introduce that fourth root, that goes back to the starred statement I made earlier. When you introduce that even root into the problem, when that even root was not in the problem in the first place, you have to account for it using a plus or minus. You do. I would have to take the fourth root, and then I would put a plus or minus in front of that radical. But again, this is not the way that I'm going to show you, because I wrote this in dry erase in orange. And I said multiple times, I'm going to erase this sucker because I'm going to show you a nicer way of doing the problem. Spoiler, the nicer way still involves a plus or minus. If I want to cancel out that 4/3 exponent, I am going to do the following. Again, under the guise of whatever I do to one side, I have to do to the other. I am going to raise both sides of the problem to the 3/4 power. Now, what that does is this. According to our exponent properties, whenever I do power of a power, I am supposed to multiply those two exponents together. And when I multiply those two exponents together, oh man, they're reciprocals of each other. Being that they are reciprocals of each other, they will cancel each other out. Boop, boop. That's the noise they literally make. Leaving you with x equals something. We'll deal with that something in a minute. But I need you to see the most important thing. The most important thing is where my marker is pointing right now. Oh, you can't see where my marker is pointing right now. Let me turn my marker around. Right there. Look where my marker is pointing. I'm going to walk up to the board just to point with it with my hand so you can see me in real life. The most important part is the fact that when you canceled out this exponent, you did so by introducing this fraction. And I've been saying it for multiple class periods, and I'm going to say it again. Power over root. When you introduced this fraction, you introduced an even root to the problem. And by introducing that even root to the problem, you need a plus or minus to account for it. You absolutely stinking do. Now, we're not done with the problem just yet. I'm going to wrap up today with this problem. This will be the last problem that I do, but I need you to see how this problem ends. And I'll recap what I did. I am going to evaluate this problem actually much easier than what I tried before with the dry erase marker. I converted it to radical form. I converted it to radical form because now I can simplify. Notice I put the cube on the outside. That makes my life easier. The fourth root of 16, if you're able to figure this out, well, what is 16? 16 is 2 times 2 times 2 times 2. That's what 16 is. 16 is 2 to the fourth power, which means the fourth root of 16 is nothing more than a 2. That 2 is still being cubed. That plus or minus is still coming down for the ride. And we get our answer. Now, I'm going to confirm this answer for you. I have to confirm this answer for you because that is actually going to be a strategy that we need to do moving forward. But I need to confirm that this answer actually works. I got 2 answers. I got a positive 8 and I got a negative 8. I got 2 answers, ladies and gentlemen. Let's confirm that it actually did work. And then I will just go through the problem one more time with you just to make sure. First of all, when you raise to a fractional exponent, you recognize that this should be power over root. Power over root. So when I plug in that positive 8, boom, I plug in that positive 8 in for the x. I'm going to take it as, well, I'm going to do the root, and then I'm going to do the power. I wonder, what is the third root of 8? Oh, the third root of 8 is 2. Okay. And then 2 to the fourth power, 2 times 2 times 2 times 2 is 16. 16 minus 5 is 11. It works. But let's check the negative. If you check the negative, let's go through it again. Plug in the negative 8 as the other answer. The third root of negative 8. Oh, man, a third root of a negative? Oh, I can do the third root of a negative. The third root of negative 8, after a little bit of digging, is negative 2. Negative 2 times negative 2 times negative 2 give you negative 8. Negative 8 to the fourth power gets rid of the negative. Oh, I'm sorry. I said negative 8. I meant negative 2. What is wrong with me today? Anyway, the third root of negative 8 is negative 2. Yes, negative 2 times negative 2 times negative 2. That works. Then negative 2 to the fourth power does get rid of that negative, but negative 2 times negative 2 times negative 2 times negative 2 does give you 16, and then 16 minus 5 is 11. We added the 5. We raised it to a reciprocal exponent. Because we introduced an even root, we needed a plus or minus. We evaluated based on everything that we've been doing for the past several class periods. We evaluated and simplified that root, and we got our answers. You will be getting an assignment from me, and I will be continuing with this stuff in the next class period. If you haven't left a comment, please do so. There's the bell. I timed that out kind of okay. I was off by like 2 seconds or something. Whatever. Shut up. Go to your next class. Like I said, if you haven't left that comment, please do so. I appreciate all you guys for hanging out with me the whole time. Everyone leave. Take your stuff with you. Goodbye. Social distance in the hallways. Goodbye, goodbye, goodbye. Take your stuff with you. Goodbye, goodbye. Leave. Bye-bye. Just say goodbye. Thank you. I appreciate that. Okay. Bye-bye. Bye-bye. Bye. I'm going to sign off. Bye-bye.